So, so it's okay. Okay, so we're gonna start. Welcome back. So I will resume where I stopped yesterday, except I changed a little bit the way I organized the lecture. Yesterday, I wanted to talk about fission observables. This was part of the introduction to fission science in general. And so after describing the fission process, I wanted to give you a list of some of the fission observables that people can measure and that theories can calculate. And I had started very briefly, I just written the first line, which, as Angela pointed out, was actually wrong. Some derivations about scattering cross sections. I decided to shift that to tomorrow, where I'm going to anyway give additional derivations about fission cross sections. So it's better to have all of them at once. And so instead, what I want to do now is talk about fission cross-section, yes, but in qualitative terms only. So if you remember the cross-section in general is the probability that something happens per unit area. So I'm just going to show you without giving you any, oops, there you go. Here is a typical picture of fission cross-sections. There are three different plots here. This is all for the special case of plutonium-239 when a neutron hits on plutonium-239. And we're going to start with the figure on the left. This shows the fission cross-section. So it's because it's a probability per unit area. It's measured in distance square, so barn in this case. And this is as a function of the energy of the neutron. And you will notice first that both axes are in log scale. And then that the x-axis, the energy is in electron volt. So it covers anything from a few dozens of milli-electron volt all the way to MeV. And now if you look at this cross-section, first of all, there is an overall trend here that it decreases as the energy of the incident particle increases. Anybody knows why? Anybody can guess why? I know it's early to be smart, but hint, it has absolutely nothing to do with fission. You have a target and you have a projectile and it's going faster and faster. The probability that it's actually captured is getting lower and lower. If the neutron is not captured, the system is not going to fission. So what we are seeing here is just the fact that the probability of absorbing the neutron is going down as the energy of the neutron is increasing. Okay. This, in fact, is known as the inverse of the velocity law. So it's essentially the cross section is inversely proportional to the velocity, that is, to the energy of the particle. Then we hit this region here where things get very complicated, and this is a region which is called the Resolved Resonances region. These are all resonant peak. This one is also a resonant peak, by the way. In plutonium, there is such a peak. In uranium, there isn't, so that will be completely nucleus dependent. But the fact that there is a region in this energy range where you have lots and lots of different resonances, that is a common feature of most of these fission cross-sections in actinides. So what happens is that for particular values of the energy of the neutron, this matches with some excitation energy of the compound nucleus, and for that particular configuration, the probability that the system fission is the probability that the neutron is captured increases, and the probability that fission occurs is thus also increased. And then as we keep going to the energy, we're going to switch to the one here in the middle. This is basically following this trend here, and now the cross-section is plotted in linear scale, but still as a function of the energies in log scale. And things get even more, in a way, gets more complicated because now the cross-section increases, although there are jumps. This particular jump here corresponds to the case where what we call second chance fission. So this is the neutron comes in, is absorbed by the nucleus, and then another neutron is emitted by that nucleus, and the resulting nucleus fissions. So we start with plutonium-239, we absorb a neutron, it becomes plutonium-240. Plutonium-240 emits a neutron, so back to plutonium-239, plutonium-239 fissions. At the same time, plutonium-240 also fissions. So this is why you have a big increase of the cross-section right here. Now, the overall patterns is not very easy to describe. I mean, there is no, let's say, general rules. This just reflects the competition between the different decay channels of the nucleus. Does the nucleus plutonium-240 decay by emitting neutrons? One neutron, two neutrons, emitting photons, fissioning. There is a complicated competition between all these effects, and the net result is this structure in the cross-section. Okay, so there is no, don't ask me why this is going up here and going down there. This, you would have to go to do the actual calculations to try to figure it out. This, in fact, even though it, well, kind of look a little smooth, what is this, this curve here is there are so many resonances that experimentally they cannot resolve them. What they see is just a sort of average of all these resonances. This is why this jagged pattern gets sort of, you know, compressed. This doesn't mean it's smooth and there are uncertainties. It just means that there are too many resonances and we don't see something like this. We just see the average. Okay, so this is called the unresolved resonance region for that reason. And then the last plot I wanted to show is these are again two different measurements and they are new. I mean, well, not new, but recent, not too old, let's say. And the only thing I wanted to show is that things depend on the experiments. It's hard to measure these quantities and there are experimental uncertainties, discrepancies between different measurements. That is a problem. If you operate a nuclear reactor, you want to know exactly how many fission are going to happen. If you make a 10% error because you got the cross-section wrong, that's a difference between your reactor providing you electricity and your reactor destroying the city because it explodes. So you really want to nail down all these differences. And this is very difficult to do. This is a theme that we are going to go through later on, actually later on today in the next few slides, when we talk about other observables. The uncertainties, the difficulty in measuring all these quantities and the difficulty in computing them and the resulting uncertainties. Okay, so this is the first of, yesterday I realized I was, when I wanted to talk about observable, I made a list of these observables and I just said, oh, there is a fission cross-section and then there's just a bunch of things corresponding to what happens when fission occurs. Fission probability, in fact, is in two categories. There is the cross-section, which is what is shown on the screens here and corresponds to induced fission, typically neutron-induced fission. But there is also the spontaneous fission half-life. This is also a probability. And so I'm going to now show you how they look like. So the this figure on the left is the chart of isotopes. And it's color-coded based on the decay mode of each nucleus. This is taken from this website here, which maintains nuclear data in the US. So in bluish, because it's not easy to read, but in blue, these are electron capture. So every proton-rich nucleus is going to decay back to stability by converting a proton into a neutron. So in order to go back towards the black squares, which are the stable nuclei. In pink, these are this is the inverse process. It's beta decay. So you're going to have a neutron converting into a proton, so that you're going left from right to left. Then the yellow ones are alpha decay. So most heavy nuclei decay by alpha decay. And then as you go to heavier and heavier systems, and this is a close-up of this region, this, you see the green, this is spontaneous fission. So on one hand, there are not that many nuclei that spontaneously fission in nature. On the other hand, they are strategically located, because this means that when you look at astrophysical processes, I'm going to show a slide in a little bit later, the mechanisms by which you make heavier and heavier elements at some point has to terminate, because you start making heavy elements that fission. And when they fission, well, you cannot go higher, and it's just, it stops there. And when you look at these green squares and you plot the half-life as a function of some indicator, which is z² over a, it's a convenient way of plotting things. This is a figure taken from this book, very nice one, by the way. So this is how the log of the half-life looks like, and this is in years. And what strikes you in this figure as a scientist? I'm not even asking as a nuclear physicist, as a scientist. You look at the figure, what do you think? You're not thinking. Nope. That's not a problem. 35 orders of magnitude, easy. Any branch of science, if you want to predict as a theorist, let's say, or actually even as an experimentalist, if you want to calculate something, in this case the half-life, that covers 35 orders of magnitude, this is going to be hard. This goes from thousands and thousands of years to milliseconds. So your calculations are going to have to be very, very precise if you want to nail these quantities. The reason why you have such a big spread is because, as we'll see tomorrow, I think, behind the formula for the half-life, at least the one that is most often used, there is an exponential. And so if you have an exponential, it amplifies everything, and that's the reason why you have these big variations. You will also notice that if you know your elements by heart, that as you go from lighter to heavier elements, the half-life overall decreases, which means spontaneous fission is more and more likely. Okay? Yeah? You start, well, you need some neutrons, so you can start in, I don't know exactly what they do in a reactor, but you just need to have some initiator, some neutrons that you can generate from a neutron source. And then you will put, in fact, I'm going to go back to this if you don't mind, because I have a figure I have a slide on nuclear reactors, so I'm going to go back to that question then. Other questions? Nope. Okay. So this covers, as far as I can tell, the only two observables that correspond to probability of fission, fission cross-sections, spontaneous fission half-lives. Anything else has to do with fission product. And fission product means we now assume that fission has happened, and we are asking, what do we see? What are the things that we can measure to sort of get information on the process? And one of the first things that we discussed already yesterday was the yields. So the distribution of fission fragments. And so I'm going to give here the formal definition of the yield. And for this, I need to take my notes because I don't want to scrape it up completely. So it is a definition. It's usually, if you remember, it's denoted by the letter Y, and it's the yield, the two-dimensional yield, so the probability that you have fragments with Z protons and a total number of particles A. Don't ask me why it's not Z and N, it's Z and A. This is going to be given by the probability that you have the fission fragment as Z particles, N neutron, given the fact that you started with a fissioning nucleus, a compound nucleus, let's say, that has Z index Cn and N index Cn neutrons, plus, and that's why it gets confusing, the probability that there is the complementary fragment that has NF prime equal NCN minus NF, and then given NCN. These quantities here are actual probabilities. That means they are normalized to 1. So it means that if I sum over Z or Z from 1 to ZCN, and I sum the neutron number all the way from 1 to the total number of neutrons I can have in my system, of that probability, ZF equals Z, NF equals N, given that gives me 1. And it also means, by way of consequences, that if I now do the same summation of the yield, then it sums to 2. Sometimes you would also find that everything is multiplied by 100 to give some kind of percentages. This depends on people's preferences, but a yield is always normalized to 2 or to 200%. And that just reflects the fact that each time you see one fragment, there is a complementary fragment that should be there as well. And it's a definition. It's the way historically it was done, and even though I usually interpret this y as a distribution of probability, it's technically not exactly true because of this normalization. So if we look at how those yields look like, here are two examples of for the same nucleus, and instead of showing plutonium, I'm showing uranium, uranium-235. This is again the neutron-induced fission. And so the figure on the left shows this quantity, the two-dimensional yield. This is in fact the cumulative yield. So this is after all the decays have happened. You look at all the products all the fission products that have been formed, and you plot their relative probability, normalized to 2, and you see that you see two things. First of all, if you look at the color scale, this is in log scale. And so there are some fragments, or some products, I should say, that are populated with a very low probability. This is, I believe, not a measurement, but an evaluation. I will come back to this, or if you want a calculation. So some of these products are very unlikely to be formed, but it's not zero. The second thing that should be striking is that there is a lot of them. I mean, there are hundreds of fission products. For the fission of uranium-235, you have hundreds of fission products. For a theorist, that means we have to get information on every one of these systems. We have to understand how they de-excite, how they decay, their nuclear structure properties. We need to understand all of this if we want to have a chance to describe what's happening. And conversely, for experimentalists, it means they have to measure a lot of different properties. This is a figure that is taken from the Japanese Atomic Energy Agency. So that's the two-dimensional yield. Now, if you integrate over n, oh yes, I didn't put the. So this is a two-dimensional distribution of probability, so you can marginalize over one or the other variable, so you can get the mass yields. I don't remember if I wrote that down yesterday, but you have the mass yield, which you integrate. I have to check my notes again. This is pathetic. Z equal 1. So if you integrate this two-dimensional distribution from over Z by imposing that the sum of Z and N is equal to A, then you get the mass yields, and then you can define the charge yield. So this is the mass yields, and this is the charge yields, which are going to be obtained in a very similar manner. So this time you're going to sum over the number of neutrons. You're going to impose that the total number of protons in the fragment is equal to Z, and you're going to get the charge yields. So this is convenient because now you can plot curves instead of plotting contour maps. And so here is an example for this very system of a mass yield. These are measurements, actually. And so this again reflects what I was saying just before, is that you have different experimental data sets and you have different results. And that may not look like too big of a difference, although you'll find, if I remember, oh no, that doesn't seem to be the case here. I thought that there was somebody who made 2 different experiments and got 2 different results. It may be another case. Even though it doesn't, perhaps it's not that big of a difference, in applications, in a reactor, you don't want to have these little differences because you don't want your reactor to become supercritical and explode. So this is, I'm going to make an aside. This is this leads to what is known as evaluation of nuclear data. Application users, people who are in nuclear engineering, people who build detectors, people who build detectors, for example, to monitor radioactivity near some sites, people who build nuclear reactors or operate them, they they are users of nuclear data. They take data like this, yields of the fission yields of some actinide nucleus or the cross sections of particular fission products and things like this, and they use that in a code that will, say, simulate a nuclear reactor. And that code will also depend on lots of other inputs, on material properties, on transport properties, but it will use nuclear data as just a regular input. The question is, if I give, among these inputs, if I have to provide the yields, which yields do I give? I have different experimental measurements. If you ask theorists to do calculation, each theorist will give 5 different curves. So now, how do you combine all of it and give a single number or a single curve to a user? And this is what is known as the process of evaluating the data. What people do is they came up with complicated processes of combining all the experimental measurements, combining the best possible models, usually introducing some parameters in the model so that we can fit to data, using statistical methods to sort of vet or disregard some of the data, and then do all this complicated cuisine to essentially come up with a best mean value and some uncertainty that users can input in their codes in their application. This is a very complex process that is extremely important, and in my to my knowledge, it's one of the few examples that is truly international scientific cooperation. Every country that has some interest in nuclear science collaborates in that, including countries that you would be surprised to think are collaborating in the current geopolitical context. So everybody believes that nuclear data is so important that when it comes to evaluating the data, we all work together. Then what we do with the data is another story, but when we evaluate the data, we work together. This is just an aside. Yes? Yes, that's exactly what I was expecting when I started working at Livermore, because I didn't come from a fission background, I come from a nuclear structure background. And then I thought, like, well, okay, I mean, fission, we know, right? I mean, we've known since 1939, we've made a bomb in 1945 and it worked. We've had nuclear reactors since essentially that 1950 or something. So yes, there's been a lot of progress, but as it will also come clear, as actually I can perhaps show it now, the second, I'm going to go back to this. And I need to go back to your question as well. So I have to keep track of everything I'm supposed to go back to. This is now one particular, a few plots showing the fission spectrum, the prompt fission spectrum. If you remember, the prompt fission spectrum, this was all the neutrons that have been emitted by the fragment. And they are characterized by an average number of neutrons that is typically noted nu bar. And it has an average neutron energy. And then there could be other things like some angular correlations between the neutrons or whatnot. And then in addition to this, there is a number of photons emitted. And again, this would be characterized by what is known as the photomultiplicity, which is the average number of photons that are emitted by the fragments. And then there would be some average gamma energy of these fragments, and possibly other things. So this is the prompt fission spectrum. Here are examples of the prompt fission spectrum. On the left, this is for plutonium-239. All the figures are taken from this paper. So this is the fission of plutonium-239. This figure here is the prompt neutron multiplicity. So this is the average number of neutrons emitted by the fragment as a function of the mass of the fragment. And then in the bottom, this is the average energy that these neutrons carry away, again, as a function of the mass of the fragment. And just like for the yields, in fact, this is more spectacular here, all the points that have some error bars are measurements, and they are very different from one another. Again, as a nuclear theorist, you may think, well, actually, it's not that different because, you know, we like big error bars. But if you operate a reactor or anything like that, there's a big difference between having 2.5 neutrons on average or 2.7 neutrons. Or having a neutron that has an energy of 0.5 MeV or an energy of 1.5 MeV. That's going to change the fission cross-section. Okay? Same picture here. I don't need to take more time, but this is the same picture for the photomultiplicity, so the average number of gammas that are emitted by the fragments. This one is for uranium-235, but you would have a similar picture for plutonium-239. And then this is the average gamma ray energy, and this one here is the cumulative. It's the gamma spectrum. So as a function of the gamma energy, you count how many gammas have been emitted in that particular energy bin, and that's what's plotted here. So now, what was the progress? If you've seen the movie Oppenheimer, which I assume several of you have, back then people got a lot of this data with bigger error bars, a lot of this data by trial and error. Let's change a little bit this, let's make a bomb and make it explode, and oh, we take measurements, okay, let's change this. So a lot of this data was indirectly obtained. The data also was, let's say, partial, so some points would be missing. Same picture for the yield, by the way. This would be, and then you would only have it for just a few fissioning systems, not necessarily for all of them. What has progressed is the level of refinement, the amount of data we have compared to what we used to have. Although at the same time, I have to say, and this may be clear if you look at some of the dates here, that some of the data is old because it was used, for example, in a nuclear test. It was obtained in a nuclear test, which many countries do not do anymore. And so from a purely scientific point of view, you are losing a particular way of obtaining data. I mean, there are other reasons why it's very good not to do any nuclear test, but from a scientific, idealistic point of view, it's a kind of experiment that you don't have anymore, okay? So we've accumulated more data, but yes, it's hard to measure these things, and so we are now so in the past. What has perhaps changed the most as well is that in the past people were relying almost exclusively on experimental measurements, and the models were extremely, let's say, approximate. Now we are really trying to simulate the decay of these fragments with our theoretical models. So that has changed also the picture, because it means we are asking experimentalists to make specific measurements that perhaps they didn't care about, but for us it's a way to test that our models are working as expected. I don't know if that answers your question a bit. And can you remind me what your question was? Oh, yes, yes. Yes, and that's when I talk about the applications, the nuclear reactor, yes. Other questions about the fission spectrum? Okay. So in fact, in terms of observables, I could also talk about the beta decay spectrum, when the fission fragments beta decay back to become fission products. I didn't include anything, but this is also something that can be measured. Is the energy spectrum of the particles that are emitted in the beta decay process. I could also talk about the gamma, the delayed gamma emission, so the emission of photons by the fission products after those fission products have decayed. Again, I did not include them. This is more of the same, complicated plots with apparently lots of data points, but those data points are very discrepant. The uncertainties are big. And the models, by the way, these are different. These are the models that they use in this paper, where they have some parameter here that they are trying to change to fit the data. And this is hard, especially because if you have to fit the curve here, let's say, these are the experimental data points. Again, the question is, what exactly do you fit to? I mean, it's not, you have to choose something. So this concludes what I wanted to say about fission observables. Should I move to the next set of slides, which are going to be purely slides now, because it's just going to finish this introduction with a few words about applications. And so first application, oh yes, sorry, yeah. Yes, I mean, they are also, if you look at the various points, so then these are either the red or the green points, there are so big fluctuations around A/2, so it's this would have to, you would have to look at the case by case. Every one of these are the fragment mass, but for even given mass, you have different combination of Z and N that give the same mass. And they may have very different excitation energy. When you're looking at the average, you sort of smooth things out a little bit. But if you were looking at every single nucleus, you may find big variations for the same mass, but as in terms of how many photons are emitted, for example. More questions? Okay, so for the applications, I have 3 slides. One is on nuclear engineering, and it's, I thought about making a slide about nuclear weapons, and then something told me perhaps it's not a good idea. We can talk about this on Friday, but in a more open discussion without recording. And certainly without any written, well, proof. So, instead the application I'm going to talk about is nuclear energy, nuclear reactor. So in the nuclear reactor, you have some fuel, which would be typically uranium or plutonium. And when uranium or plutonium, it means uranium-235 or plutonium-239. Now, I do not know exactly how they start the chain reaction. If you remember the plot before, this is the average, where is the multiplicity? For plutonium-239, this is the average number of neutrons that are emitted, and per fragment, if you do the average, you find that one estimate is about 2.7 neutrons are emitted in the fission of plutonium-239. Which means that at the first generation, you have your initial amount of plutonium. You initiate the reaction somehow by shooting neutrons at that. You're going to trigger the fission of plutonium. Then, on average, 2.7 neutrons, which of course means either 2 or 3, but not 2.7, are going to be emitted. At the second generation, you're going to have more fission. And then it continues like this, and it grows combinatorially and very quickly. At the 20th generation, you will have a lot of fission happening. Now, if you think 20th generation is way too much, remember the fission timescales? It takes 10 to the power minus 19 seconds to fission. It takes about 10 to the power minus 15 seconds to emit neutrons. So it's pretty easy to get to 20th generation in a nuclear reactor. So what they do to avoid big problems is that they, in the reactor itself, they will put moderators. Typically, I mean, the technology that I'm familiar with is a big word, but the one that I remember is you put graphite tubes that will absorb the neutrons. So you will have plenty of neutrons emitted during this fission. What you're trying to do is to maintain the number of neutrons that are flying away to be constant. So you make sure they don't, that number doesn't grow too large. So you absorb some of them, you make them disappear, you remove them from the reactor, and you do this by making sure they will be absorbed by some of these moderators. So the absorption cross-section of neutrons by carbon, which is graphite, is pretty large, and that's a way to absorb those neutrons. And they will move the graphite tubes away or back in or back out to make sure that everything is more or less constant. If they put too many graphite tubes, what happens is all your neutrons get absorbed after some time, and the number of fission decreases, and at some point there is no fission happening anymore. If they don't put any moderator, it explodes. And so they are trying, and so if the number of fission dies, then if your number of neutrons is too low, you are subcritical. If your number of neutrons is too high, you are supercritical. That's indeed supercritical. And if you have just the right amount, you're critical. And people who operate those reactors and the ones who design the models to see how those reactors behave spend a lot of time to make sure that everything stays critical. And there is a quantity called the criticality factor, also known as K effective, which has to be exactly equal to 1. And people spend a lot of time to design things so that this is the case. In fact, another aside, in the process of doing that, they will change the nuclear data we give them. People spend a lot of time making measurements, very fancy calculations to match the measurements. They gave that to the people at nuclear reactors. The first thing they do, they check that this data is compatible with what they see in the reactor, which is K effective equal 1. If it's not compatible, let's change the data. We change reality to match another form of reality. It's a very weird thing if you think about it, but that's what people do on a daily basis. So that's for nuclear energy. Now let's go back to science, safe ground. So first application of fission is pretty obvious. It's super heavy elements. Why? Because as I mentioned earlier, as you make heavier and heavier systems, at some point you hit the region of spontaneous fission, and so that will limit how far you can go in Z number. So this is the latest version of the periodic table of elements. The heaviest element that has ever been made is oganesson, named after Yuri Oganesson from Russia, with 118 protons. And the question is, can we go even higher? I mean, this oganesson sort of terminates the noble gas column, but can we make another row perhaps? So for this, people will simulate, and I'm sorry, but I forgot to put the reference from where this figure is taken. People will calculate the various decay modes of super heavy elements, and they will look at which one is dominant, and then they will make predictions based on that. And based on those predictions, experimentalists will see whether, which nucleus is perhaps the most interesting to try to make in the laboratory and try to study. So this is one such calculation where in green are nuclei that are predicted, this is a prediction, predicted to mainly fission, versus when it's not color-coded, it will decay by alpha decay. So that's one application, super heavy science. And then the other application is nucleosynthesis, and I already talked several times about that. The rapid neutron capture process that takes place typically in a neutron star merger. That's a hot topic these days. It may also take place in supernova and other exotic types of merger, like a neutron star, black hole, and these kind of things. So you have, in those environments, you have zillions and zillions of neutrons. You have a huge neutron flux, and so you also have nuclei which will absorb those neutrons. So you will absorb neutrons going to the right, until you become unstable and beta decay back to higher systems and keep absorbing neutron, and so you will zigzag like this all the way to the heaviest systems up to a point where you reach, again, those spontaneously fissioning nuclei that will terminate the process. And there is also a speculation, it's a bit more than a speculation, I guess, that if you remember the distribution of fission products was covering a pretty big chunk of the nuclear chart. So when those heavy systems fission, the fission products are re-entering the reaction network, the networks of reaction that are happening, and so that should in principle be taken into account by the people who do the simulations. So here are figures taken from these two papers by some of my collaborators of old and of new. This one is from the last person we hired at Livermore, where they did simulations of the rapid neutron capture process with a decent fission model. Decent because it's still, there's a lot left to, it could significantly be improved, but it was a major improvement over past calculations. And so they found that they were able to kind of reproduce observed abundances by having sort of semi-realistic predictions of fission product yield. They also suggested in this paper that if you wanted to match the elements, the abundance of elements observed in some stars outside the galaxy, not in our solar system, you had to sort of increase a little bit the role of fission in this R process. So this is a question back to fission theorists, is can you explain why we need more fission that seems to be by default, so to say. So this is another application where things like fission yields, fission rates, so fission rates is the inverse of fission probability, are very important for this kind of simulations. Although to be fair, for our process, every nuclear data is important, whether it's fission, capture, scattering, anything, they need to know everything. Questions? Yes? So the simulation, these kind of simulations, the R process, or which? So in a R process simulation, you need two kind of inputs. You need an input that corresponds to the astrophysical scenario you're trying to describe. Let's say a neutron star merger or a supernova explosion. So they will need to know things like the temperature, the pressure, the energy as a function of time. And so that's one set of inputs. And then they need to know everything about every single nucleus, the excited states, the decay rates, all the decays, neutron, gamma, beta, alpha, all the letters of the Greek alphabet, everything, even neutrinos, interaction with neutrinos, because those reaction rates are going to be coupled. I mean, you're going to basically set up a big system of differential equations. That is, for every single nucleus, is what comes in, what comes out. So what are the processes that lead to this nucleus? And what are the processes that take you out of it into another one? And you're going to solve that as a function of time. And so that's the kind of simulation they do. Yeah. Yes, so that's a very good question, actually. There is a few years ago, about I think 10 years ago now. So in the fission process, perhaps I can go back to one of my initials from this slide. So I did mention the beta decay, that's the fission fragment beta decay to give fission products. In beta decay, yes, you turn a neutron into a proton, but you also release antineutrinos. So it's N gives P plus electron plus antineutrino. In a reactor, therefore, you have lots of antineutrinos that are emitted. You have a huge flux of antineutrinos. And what people found out is that there was a little discrepancy between the amount of antineutrinos they were expecting and the ones they were observing. This was fraught with uncertainties again, because it's not easy to detect neutrinos, especially, well, next to a reactor. But there was a mismatch, and the question was, is that caused by some physics beyond the standard model, that they are sterile neutrinos, or I don't know what, some exotic scenario, or is it caused by something that is missing in our description of fission? Now we are converging towards that second hypothesis, that most likely the beta decay spectrum of the fission products is not correct. I mean, we are missing some information, and so we got at that indirectly through detection of neutrinos, or actually lack of detection of neutrinos. Does that answer your question? Yeah. More questions? If not, I'm going to move to the second part of that of my 4-block lecture that is going to be spread out of 5 sessions probably, which is how to go from nuclear structure to nuclear fission. Until now, I was very qualitative. I wrote a few things on the blackboard, sorry, but that was quite simple. Now we're going to get a little bit more into specifics. So for example, when I was talking about deformation, I didn't specify like what exactly is that deformation, what parameters, I mean, how do I calculate this? We're gonna get into this now. Okay, so how do we do calculations to make fission calculations? Before I do this, though, I realized I wanted to mention what are some of the takeaways of this first introduction. The takeaways, as I think they should be your takeaways, but perhaps you will remember something else. So one of the takeaways is, roughly speaking, 2 main fission mechanisms: induced or spontaneous. Induced can be by neutrons, can be by photons, can be by beta decay or anything, by electrons, but induced and spontaneous. Second thing, the physics of fission. This is not just I split in 2 and that's it. There is a lot more things going on, a lot more data coming out, plenty of fission products. Each of them has emitted plenty of things. So there is a lot of things behind the world of fission. Okay, there are probabilities, products, all different things to calculate and measure. So that's the second takeaway. A third takeaway was the list of some of these observables. I mean, you don't need to remember all of them, but if you remember a few of them, that would be cool. This is what we can measure. And then the fourth takeaway, and last but not least, is that fission is really understood these days as it was back in 1939 as a deformation process. The nucleus deforms itself. Why is that a big deal? When you guys were introducing yourself, some of you said I work on the no-core shell model. In the no-core shell model, there is no deformation. people who do regular shell model or any other kind of many-body methods, Green's function, couple cluster, quantum Monte Carlo methods, they don't need deformation to describe nuclear properties. As a matter of fact, a nucleus has a good angular momentum, which means rotational invariance is preserved, which means the nucleus is not deformed. Deformation is a model-dependent concept. It's a theoretical concept that we introduce to better understand the world as it is showed to us. In fission, that's really how we understand the process. But this is a pure theoretical construction. So if some of you are really very, very smart and into hardcore nuclear theory, how could you describe fission without introducing any deformation? Good luck. Okay, so now to the second part of the class, which is going to be titled, because I put a title. So it's, we go from nuclear structure to fission. And there's going to be, it's going to be essentially, again, divided in two. I'm going to talk about nuclear, what I call now, these days, phenomenology. And thanks to Professor Meng yesterday, we talked a little bit about the leaky drop and the shell correction. This is my way of saying the microscopic model, or also known as leaky drop model plus shell correction, sometimes also known as a finite range droplet model. All these are different words that a certain way of describing and computing nuclear properties. And then the second part is going to be about energy density functional method. Also known as EDF. And for the experts in the room, this is the single reference version of it. And on Thursday and Friday, we're going to talk about the multi-reference version of that. So this is also known as self-consistent mean field theory. R-Trifog, and that kind of thing belongs to this family. This is also sometimes simply called density functional theory. In the past, so this is an aside and that's my personal opinion, disclaimer, until 1998, people were talking about it as self-consistent mean field theory until Cohn in chemistry got the Nobel Prize for density functional theory. And then nuclear physicists like, wait, we also do the exact same thing. Let's call it density functional theory now, except with nuclear in front of it. So, but this was really self-consistent mean field. Okay. So let's talk about the first part here, and this is, I'm going to write again the leaky drop formula. So I'm going to start with this. I'm going to put again the leaky drop formula that we saw yesterday. And so leaky drop model. Oops. And this is the simplest version of it, which is spherical, and it's just the drop. It's not the droplet. And the simplest version of the leaky drop model, the binding energy per nucleon is a constant term, which is the volume term, and then there is a surface term, which I never remember which exactly is the dependency. Minus. Then there is a Coulomb term, which is z square. And then there is an asymmetry term, which is n minus z, divided by a square. So we've seen that yesterday in the lecture of Professor Meng. This is the historical Bader-Weizsäcker leaky drop formula from 1935. A few words, this A volume, A surface, A Coulomb, and asymmetry are parameters. as parameters. One way to determine their values is just to fit the formula on experimental data. We have the binding energy of nucleons. We have the results for hundreds, if not thousands, of nuclei. So we can make a fit and then come up with values for these four constants. This one is attractive. So the bigger the nucleus, the more bound it is. But then the three other terms are repulsive, so they have different signs from this one. If in a nucleus, the nucleons that are at the surface of the nucleus are less bound than the ones that are deep in the middle. So that's why you have this repulsive term from the surface, just like a drop. This is obvious. This is Coulomb. You have protons closely packed together, so there is a Coulomb repulsion. And then this one comes from the Fermi gas model. If you put two different species of particles, if you remember the Fermi gas model from quantum mechanics 101, or well, first class of quantum mechanics or something like this, you put particles in a box and you count how many states there are per unit cell and things like that in phase space, then you can come up with this term here. Okay, so that's the spherical version, but in fission, we don't care about the spherical version too much because, as I've just said, this is all about deformation. How do I change this if I want to introduce deformation? Well, the first thing I need to define what this deformation is now, because now I'm not qualitative, I'm trying to make calculations. So I'm gonna show one particular formula for the radius of an arbitrarily deformed object. So we have, let's say we have a radius here, and if I remember, this is theta, this is phi, and this would be the radius, and then this is x, y, and z. So if you have an object, if you have a reference frame like this, and you use spherical coordinates, then you can write what is known as the multiple expansion of this radius, and it's going to be something like this. So you have an expansion. This R0, we also saw that yesterday in Professor Meng's lecture. This is a small R0 a to the third, and it's one simple estimate of the radius of the nucleus. As we know, it's not very, very precise, but it's more or less gives you a ballpark estimate of what it is. Then these guys here are the deformation parameter. So these are things that we have to specify. If we want to make a calculation with the leaky drop model, we have to decide what the deformation is going to be. We have to set the value of these deformations to whatever we want. So in practice, we're going to consider different options. I'm going to come back to it, but these are inputs of the calculation. You first specify the shape by setting up what these deformation parameters are. This, okay, now it's not very visible, but this is a y lambda mu of theta and phi. This is well-known spherical harmonics. You can Google them. These are functions of theta and phi. So this is relatively standard. Yes, and then this last term is a function of those deformation parameters that guarantees, so it's going to change as a function of the value of those deformation parameters, and that guarantees that the volume of the deformed object remains constant. As you deform the nucleus, the volume doesn't increase or doesn't shrink. The volume is constant. Why? Anybody knows why? Yes, I think I heard vaguely. Incompressibility. A nucleus is incompressible, so if you expanded the nucleus, the pressure would go down. That is not possible. So the volume has to be constant irrespective of the shape, and that's going to be taken care of by that. If you want to parameterize a deformed shape, there are many other parameterization that you can come up with. This one is the simplest one to present. It's also one that has a nice mapping with when we are going to talk about this energy density functional methods. So this is why I'm presenting it. In the context of fission, it's actually not the best option, really, because it turns out that this is not a bijective function of the parameters. So you can have different combinations of deformation parameters that lead to the same radius. That's bad. So at large deformation, it's not really a very great expansion, but it's an easier one to understand. So if we now look at some of these deformation parameters, so we have, if we want to build axially symmetric shapes, then we will take deformation parameters that are that vanish if mu is not equal to 0. So if we have deformation parameters, if we only take deformation parameters with, sorry, it's an alpha, with the deformation parameters lambda 0, then the shape that we get out of this, so we basically cut this summation here, we only take mu equals 0, then the shape we get is axially symmetric. Okay, so this is axial, this enforces axial symmetry. If we take, lambda, if we take all the deformation parameters that have an odd value of lambda to be 0, then we enforce reflection symmetry. That doesn't come out of the blue, that comes out of the properties of the spherical harmonics. It's just the way it is. Okay, so that will enforce that you have reflection symmetry. And if you remember yesterday, we were talking a little bit about it when I was saying that if you want to build a model of the fission fragments that lead to a heavy fragment and a light fragment, you have to have a shape of the fissioning nucleus that is reflection asymmetric, which means you would have to include those deformation parameters with lambda that are odd. Okay, that would be a way to get your reflection asymmetry and therefore to get a big fragment and a light fragment. And then the last one is if lambda equal 1, that actually corresponds to translation, which is why the summation here, it's extremely poorly written, but it starts at 2, because the first parameter, lambda equal 1, this just corresponds to a shift of the center of mass of the system, so it doesn't change the deformation, it just shifts the system. So if we really want to look at deformation, we have to remove that parameter and put it to 0. So if we take alpha 1 mu equals 0, this means that the nucleus is localized, or the center of mass of the nucleus is localized at the origin of the reference frame. So once we set the parameters, those deformation parameters the way we want, how many we want, we define our shape like this, and then we can see, okay, how should I modify the leakage drop formula? This term here, this is a volume term, and I just said the volume is constant. So is it going to depend on deformation or not? It's not going to depend on deformation. So this one is not going to be affected. The surface, is it going to depend on deformation? Yes. That one is because, well, that's a surface, so if my surface is a sphere or if it's something different, that is going to impact this term, not necessarily the coefficient, but the term itself. Coulomb, is Coulomb dependent on the deformation? If the Coulomb energy depends on the deformation of the charged object? Yes? Okay. I know electromagnetism was not my cup of tea either, but it does. And then that term, take it for granted, it doesn't. So in practice, this means that if we take a deformed liquid drop. The formula is a little bit modified, and now we have still the volume term, which is unchanged. There will be the surface term, and there will be a function here, which is going to be a function of my deformation parameters that multiplies the, what is it, a to the power minus 1/3. Then there's going to be the Coulomb term, and there's going to be another function, again, of my deformation parameter that multiplies z square a minus this, plus the asymmetry term, which remains unchanged. Okay, we've made progress. Now the last thing is to calculate this. So I'm not going to do it. Let's see, I got here. I'm just going to outline how we do it because the details are not that important. So Enrico, I want to finish this, do the shell correction, and then make a break. Oh, are we the, okay. Okay, okay, sounds good. You heard it, it's not me. Huh? Okay, so what are those functions here? Bs of, which is a function of that deformation parameters. Well, roughly speaking, this is a ratio between the area of the deformed surface and the area of the sphere. Okay, so this is going to be surface, or area, I should say, area of the deformed object divided by area of a sphere. Well, area of a sphere, that's an easy one because they have different ways. Either you remember your nuclear physics 101 and you have a radius, and what's the radius? What's the area of a sphere given a radius? Or you take also that formula here, you put all the alpha lambda mu equals 0, and again you get the same radius. So this, the denominator, yes, is going to be 4 pi r0 square, right? Yes. Now the numerator, that's technically it's the integral over the surface, so it's, yeah, you have to do some differential calculus now, and I'm not going to do it. I'm just again outlining the overall thing. So you can replace R0 by this little formula that we had. So it's going to be the integral over the surface, and then this is going to be a, yes. This is assuming that R0 is still this guy here. And then if you want to like go one step further, you can try to plug in, you know how the surface is parameterized with this radius. So you can try to plug that in. And I'm just going to write down the integral, but I'm not going to do the calculation. So this is going to be 2/3 square, and then so now we have to do an integral over the, we have two angles, so we have the phi angle, 0 to 2 pi, then we have the angle over theta, which is 0 to pi probably, yes, and then d theta, and then we have our radius square, and then the, oh, there you go. And so if you replace the radius by this expression, given once you can write a code that will calculate that for you. If you know the value of the deformation parameters, well, you can calculate then this function here by writing this little code, okay? Or if you have some specific surface that have very nice properties, you can perhaps do it analytically as well. So for Coulomb, it's going to be pretty much the same picture. It's going to be the ratio of the Coulomb energy of the deformed object divided by the Coulomb energy of a sphere. Here it gets a little more complicated because, well, you have to calculate the Coulomb energy of the deformed object. So this would be, I'll give the result just as I found it in some book. I forgot which one. I think this was something like this. A minus 2/3. Oops, sorry. And then you would have an integral, a double integral now over the two variable, and then just a Coulomb. And this could be, then you have to go into an electromagnetics textbook and figure out how to do that. But the spirit is pretty straightforward. Once you have decided which deformations you want to include in your calculation, you have fully defined the radius of your deformed object. You can then calculate those two functions, and you have the value of the, what's written here, the value of the leakage drop energy for that deformed drop. You can go into search into the literature. People, I think you mentioned yesterday that people have made refinements over the leaky drop. They've added some term to account for the fact that the drop doesn't have a sharp surface, but it has a diffuse surface. If you do this, this adds term in the calculation that becomes also that you have to include when you deform the object, and that makes things a little bit more complicated, but it refines the predictive power of the theory. Okay. Well, that's a leaky drop. That's very nice, but it's just half of the story. I think I want to keep. Okay, no, I'm going to remove this because we've known, and again, I refer to Professor Meng's lecture yesterday. We've known since 1950 that a nucleus is not just a leaky drop. There are protons and neutrons inside. Those protons and neutrons, in the first approximation, can be thought of as independent particles that are sitting in some potential well. And this is what earns Mayer, Goppert-Mayer, and Jensen their Nobel Prize in 1950. It was called back then the shell model, but it has nothing to do with what we call today the nuclear shell model. It was actually the independent particle model that they invented back then. So you have an average nuclear potential that looks like this. This is for the neutrons. If you had the protons, it would be slightly higher, and then you would have the Coulomb barrier. And then you have your single particle spectrum, say like that. And you have your nucleons that are sitting in that potential. And depending on the structure of those single particle states, you could find particular configurations that are more stable than others. This would be typically the case if, let's say, you have all your occupied states up to that point. I am really terrible at drawing anything. And then this would be, the rest of the levels would be empty. There is a large gap here. And because there is a large gap, it means if you want to excite such a system, you would have to give enough energy to promote a nucleon from here to the first available state, which is higher than in other systems. So the shell correction technique that was invented in the 60s by Stutinsky and collaborators is a way to quantify the effect of the distribution of single particle states and occupied single particle states on the binding energy per nucleon. So in order to calculate the shell correction, I'm going to again outline how you do such a calculation. You need to get these things. You need to get single particle levels. What does that mean? It means you have to solve the Schrödinger equation. It always starts and ends with the Schrödinger equation, or sometimes the Dirac equation. But so you take the Schrödinger equation. This is now the Schrödinger equation for a single particle, and so it. Actually, you know what? I'm going to put I'm going to write it like this because in most of my notes and in most of this week, I will not talk too much about the spin because it just adds more difficulties, but sometimes it doesn't make too many changes, doesn't make things life too complicated, and therefore this is one of these cases. So in this case, I just included, just to remind you, the potential may depend on the spin, and then the wave functions of that single particle, of that single proton or neutron, also has a certain spin. This potential, this is this guy. In fact, it typically has two components. One is a central potential, which really corresponds to this average mean field. And so expression for this central potential would be a Woods-Saxon potential, a Nilsson potential, the folded Yukawa potential, a square well. That's a bad idea, but okay, it's an example of such a potential. And then there is a spin orbit term. And that spin orbit term is itself proportional to the gradient of your potential, scalar product, the spin, and the momentum of the particle, so the gradient. So this is an operator. So if you know you have parameters that characterize this central potential, and usually, even though this is a gradient, so originally people were using the gradient of the central potential, but then they realized if they change the parameters of the central potential and add separate parameters for the central part and the spin orbit, they would have more predictive power. So that's in practice what happens. So one example of the central potential, just to fix the idea of where the parameters are, I'm going to give the Woods-Saxon potential in the case of spherical symmetry, because it's simple like this. This is going to be something like this: 1 plus exponential r minus r0 divided by a0. 1, 2, 3 parameters for the central potential. Just like the parameters of the leaky drop, these are not given by theory. You have to fit them on data. How would you do that? Once I will show you how to go from the solution of this equation to the shell correction. You would add the shell correction to the leaky drop. You would calculate the binding energy per nucleon, and you would fit that to the data with all the parameters that you have. So let's see now. I can go there. So once you have solved the Schrödinger equations, you write a little code to solve the Schrödinger equation for this potential. You should modify these expressions if you want to account for the deformation. This is a little bit more complicated, but nothing outrageous. So you modify that a little bit, and then you've got your single particle states. Or single particle energy. And these are the single particle energies you're going to use that you're going to input in the shell correction recipe. And it's really a recipe. It's completely empirical, but it works beautifully. Let's see what exactly I want to say. Yes. So the shell correction, which for some reason is often written like this, I don't know why, is going to be defined as the sum over some set of the single particle energies minus a smooth energy. This n in some set I, if you're interested in the ground state properties, this is just going to be the lowest occupied states. This sum is going to run from 1 to the last occupied state, and that's it. If you want excited states, then you're going to take a set that is a little different. But for the ground state, let's make it simple. For the ground state, you go from 1 to the last occupied state, which let's say is the Fermi energy. Okay, so how do you calculate this? So the philosophy to calculate this is to say, I have my density of states, and my density of states, of single particle states, this is just This is just this. This is a Dirac comb of, you have that's your distribution, that's your density of states. It's the sum of all these Dirac functions. Now that smooth term, I will calculate it by trying instead to turn this into a sum of smooth function yet to be determined of the same difference E minus En. Okay, so the question is how, or the shell correction recipe is how to calculate that. Oh yes, and once you have this, the smooth energy is going to be the integral from minus infinity to the Fermi energy of this is going to be defined as G. So you would have a density of states, and you're going to integrate. You're going to calculate the expectation, the average energy by doing this integration here. So it all boils down to, if I can calculate this, or if I come up with a prescription for that term, then I can calculate that smooth energy. I know already what my single particle states are because I solved the Schrödinger equation, and then I can calculate the difference, and that will be my shell correction. I had plenty of notes to say how to do this. This is very boring and probably not needed. So I will skip this. You can, when I will make the material available for you, there will be references to where these things are defined. How to calculate these functions. This was invented in the late 60s, and let's say up to 1972 or so. And there hasn't been really any progress since then. This is a recipe, it works, and as a proof that it works, oh no, I thought I had a slide, but not yet. So as a proof that, well, as a kind of proof that it works, if you calculate now the total energy, which is for a given nucleus, is going to be, actually, let's put it like this, it's going to be a function of the number of protons and neutrons. It's going to be a function of the deformation parameters of your shape. And this is going to be the leaky drop energy for this particular nucleus and this particular deformation, plus the shell correction, which again is a function of Z and the deformation parameters. If you calculate, so now we can count how many parameters we have. Here we have 4 parameters. Actually, plus 1 if I count the little R0. Here you have, if you take this form here, you have 3 parameters for the central potential, and then you would have another 3 for the spin orbit. Take my word for it. So you would have, in the simplest version here, you would have 6 parameters. So you have 11 parameters total that you have to fit somehow. And again, you can calculate that and fit on data, on binding energies. You can set up the problem and do a fit of, you have to a scalar function of 11 parameters. These days, this is a piece of cake. Of course, back then when it was invented, that was not so easy. So they did a fit in 2 steps. They first fitted the leaky drop term without the shell correction, and then they fitted separately the parameters of the potential. And then once they did that, they sort of tweaked everything together. Yes. Yes, there is a couple of numerical parameters that corresponds. There is one that corresponds to the so-called smearing width, and there is another one which doesn't really have a name. It's some kind of energy scale. They are typically not fitted to data. They are set based on some convergence criterion. So you have to make sure that something is stable with respect to changes, and that's how you would set up those 2 extra parameters, 2 or 3 extra parameters of the Straczynski procedure. So in that sense, it's not really it's not really a physics parameter. It's not something that you will try to fit on experimental data. It's something that you will just try to determine numerically. 3 here, and then you would take 3 different, you don't take the central potential here, you would take the same mathematical form, but there would be 3 different parameters. That's, you would have a different spatial form factor for the spin orbit with different parameters that also need to be determined. Yes, it would be fitted different. Yes, it would be taken as a different R0. Correct. There is an R0 here, and there is another one here corresponding to the surface somewhere. It's not the same R0. Other questions? Yes. So the question is, if you take really the gradient of central potential, then you go from 6 to 3 parameters. That is absolutely correct. Then your the quality of your, this is known as the macroscopic model. Macroscopic, this part. Microscopic, this part. The predictive power of your macroscopic method would be a little less. The parameters are, as usual, when you have parameters, you can fit to data better. More questions? So, so as I said in the introduction to this, or when I started talking about this, how to go from nuclear structure to nuclear fission, I said that I wanted to show how we could compute things and how we would use this nuclear structure theory methods for applications to fission. So in the case of fission, if we want to calculate the energy as a function of deformation in the microscopic method, we do that we consider different shapes, lots of different shapes, as many as we think are relevant. I'm going to come back to it later. And then we'd calculate the binding energy as a function of those shape parameters, and we would get some potential energy surface. If we have, I don't know, 5 parameters, it's going to be a 5-dimensional surface. And then we could extract information about fission barriers from that, or fission probabilities as well, and things like that. So if there are no more questions, then I'm going to go to the other way to do these kind of calculations, which is not, so I called it nuclear phenomenology because it was historically what was used all the way to, it's still used today, it's still actually very useful, but it's not, we can do better, we can do more. We can try to get these things not by just some mathematical function that we fit to data, but by explicit knowledge of nuclear forces between protons and neutrons inside the nucleus. And we can calculate the total energy without necessarily breaking it down into a leaky drop term and a shell correction term. We can calculate something that has these 2 effects built in, but emerging from forces between protons and neutrons. And that's what DFT is going to allow us to do. And so I can now... Okay. So as we progress in our week, I will have to write more and more on the blackboards, and the equations are going to be getting a little more and more involved, let's say. And so you would have to slow me down if you think I'm going too fast, or if you think you don't understand what I'm writing down. And if you think I'm going too slow, well, please, by all means, I can go faster. I can always go faster. So if we try to calculate the binding energy of a nucleus from first principles, it's very ambitious. The starting point is a many-body Schrödinger equation. So this is the single particle or one-body Schrödinger equation. Now the many-body one is schematically, so this is many-body. So this is an operator here, and I'm going to write it using this Dirac notation. This object here, this is, so everybody is familiar with the Dirac notations, right? Yes. Yes? The ones who are not familiar and don't speak up, it's on you. So This is the wave function of, or the state vector for the full nucleus. So this is a function of all the coordinates of every single, of all the nucleons. And then this is an operator that acts on this object, and that's the energy. So you're looking for the, the Schrodinger equation, you're looking for the spectrum, the eigenvalues, and the eigenfunctions of that operator. And then this operator is typically decomposed into a kinetic energy part and some nuclear potential. So there is a two-body potential in nuclear physics, but there is also a three-body potential, and there is a four-body potential, and there is a five-body, all the way to a-body potential. That's, by the way, the fundamental difference between a nucleus and an atom. In an atom, the many-body potential is just the kinetic energy plus the Coulomb potential, which is two-body only, and that's it. There is also one body term for which is the Coulomb interaction between the nucleus and the electrons. But the Hamiltonian for atoms in electronic structure theory is much simpler than in the nucleus. In the nucleus, you have in principle all those terms. And there are people, and some of you may be working with these people, who try to calculate those potentials. We can go one step further. The kinetic energy is going to be the sum of the momentum divided. So I'm assuming that they all have the same mass, and this is the sum of the momentum square of each of the particle plus the two-body part. And then I'm going to forget about the three-body and higher terms because let's try not to be too complicated. So we are going to use that many-body Hamiltonian as our starting point. And in fact, I'm going to go one step further. I'm going to assume that plus, so this is going to be a sum of all the interaction between particles at points Rk and Rl. And I think there is a factor 1/2 if I remember, or perhaps not. Okay, so now this potential here, as I said, there are people, there's a class of theoretical methods that try to determine what these potentials should be based on quantum chromodynamics. And the way to connect quantum chromodynamics and nucleons is via chiral effective field theory these days. So there is a whole area of research, chiral effective field theory, that tries to build those things from scratch, so to say. In energy density functional theory methods, we take a different approach. We're going to approximate that. We're going to set what the form of this potential should be. So you're going to hear, I think, more probably on this week from Professor Meng about the relativistic version of that, which is yet another way to do it. So this doesn't start from a Hamiltonian, but you can get to a Hamiltonian like this. And there are different ways of building relativistic mean fields and potentials. In the non-relativistic case, the two most known form for these potentials are the so-called Sturm and Goni interactions. So these are just the two most common ones. That doesn't mean they are the only one. So and I guess I could write down the form of these, but this would take me a while, and I don't want to waste time doing it because you can also Google it and find the expressions pretty quickly. I just want to say that this depends. So I will write the schematic form of these objects because actually, in fact, this is instructive. So the Sturm potential is a zero range interaction. So first of all, this is proportional to delta or R1 minus R2. So this is Sturm. The Goni potential is proportional to, as a finite range, and so this is proportional to R1, R2 divided by some range mu square. So that's the first difference between these two, is one has a zero range and one has a finite range. Both are what are known as local potentials, meaning that these are two-body forces, but they only connect, they do not depend on the neighborhood of each potential. In other words, a most general two-body force should be something like this, R1, R2, and then R prime 1, R prime 2. That's the most general two-body force you can build. Those two are local, meaning they also are proportional. I should have, they are proportional to R1 minus R prime 1 and R2 minus R prime 2. Zero, so local, zero range, local, finite range. A few more things about those potentials, some of the necessary features that they should have, whether this is Skirm or Goni or something else, you always need some of these generic features. So either your Skirm or Goni, so your two-body force. This is going to contain a central part. It has to contain a spin orbit part. This has to be put by hand as well. That's one of the advantages of using a relativistic theory, is that these things come out naturally of the theory. In non-relativistic version, you have to put it by hand. Then, because we are restricting ourselves to two-body forces and we don't include higher body terms, in order for the theory to work like that, we have to add a density-dependent term, which is something weird because it's proportional to the power of the density. It's a source of grief because lots of technical formal issues come out of that. But right now, without this term, the theory doesn't really work well. And then that's it. So the central, now I can perhaps write down the central part for Skirm and Goni, just to mark the difference. So for Skirm, this is going to be something like this. No, I'm not going to do it. This is going to take too long, and then I would have to explain the meaning of everything. So it would be a waste of time. Does not really needed. So two-body potentials, a central part, a spin-orbit part, a density-dependent part. Each of these is driven by a few parameters. And just like in the macroscopic model, these parameters have to be fitted on data. And as an aside, I like asides. In nuclear physics, whatever you do, whether you're trying to build the most fundamental theory of nucleons, nuclei, nuclear forces, or whether you're fitting directly to experiment, you always have to fit something. Always. Nuclear physics is always phenomenological in that sense. Even the people who claim to be, who do things ab initio, are still fitting parameters to data. This is just a comment. Okay, so now we have our potentials. That means our Hamiltonian is defined. Now, how do we proceed from there? So I'm going to start first talking about the Hartree-Fock method. So for those of you who know, I'm going to try to show you to derive the Hartree-Fock equation without using second quantization. It's just because, well, let's say it minimizes the difficulties. So Hartree-Fock, which is going to be not yet the exact building block of energy density functional methods. Energy density functional methods are going to be built out of Hartree-Fock-Bogoliubov. But to understand Hartree-Fock-Bogoliubov, you need to understand Hartree-Fock first. So Hartree-Fock is a method that assumes that now, for this Hamiltonian, with those two-body forces, we are not going to solve the eigenvalue problem. We are going to postulate that the wave function, the full wave function, so it's a wave function, and I don't write down the spin degrees of freedom, but they should be there. So it's a wave function of all the vectors and the spin of all the A particles. So we're going to write it down as a determinant of single particle wave function. And I think it's why do I write it down as a determinant? Anybody has an idea? Oh wow, you have plenty of ideas. Like, oh, okay. One more time. Anti-symmetrization. Yes, a determinant changes sign anytime you do a permutation of its components, and so this reflects the fact that our system is made of fermions. Fermions obey the Fermi-Dirac statistics, so they should obey this relationship that when you permute anything, you change the sign. That's what the determinant ensures. Okay. Now those objects are single particle wave functions that depend only on one space and spin degrees of freedom. And so we are going to use those functions. They are unknown, and we're going to try to find what they should be in order to minimize the total energy of the system. The total energy of the system at the R3 Fock level is going to be calculated by something like this. You take your Hamiltonian, you take your ansatz, your wave function, your postulate for the wave function, you calculate the expectation value of the Hamiltonian, the many-body Hamiltonian. In case this was not normalized, you divide by the norm, but okay, and you get your energy. And that now this guy is a functional of all the single particle wave functions. It's a functional, meaning it's a function that depends on functions. And I can say, well, if I minimize this energy with respect to all these wave functions, I'm going to assume that I'm going to decide that this is my solution. The best wave functions, the best single particle wave functions that ensure that my many-body state is a good solution to the R3 Fock problem. The best wave functions are the ones that minimize the energy of the system. Okay, if you think this was getting a little too mathematical, it's going to get worse. And as it gets more mathematical, the probability that I start making mistakes increases dramatically. Oh, yes. Yes, well, actually it's hidden there, right? Because I take all the A particles, so some of them are protons, some of them are neutrons. So I could actually I should label that with the spin and isospin degrees of freedom. Where is it? So both the Skirm and the Goni terms, the Skirm and Goni forces, they have terms that depend on the isospin, especially the isospin exchange operators. So yes, it should be taken into account, but this just makes the formalism so much more complicated. I mean, not that complicated, but it's supposed to be on fission. This is just a tool to get to fission, and I don't want to spend too much time on that. But you're right, yes, the isospin degrees of freedom is there as well, just as a spin degree of freedom is there. Questions? Yeah. That's, yes, absolutely. I will have to seriously adapt my my course material, I think. No, yeah, it's good. Yeah, it's fine. No problem. So after, I mean, tomorrow we're gonna I probably will not show as much as I wanted to show. I wanted to derive really the whole, like, say the energy is minimal and what does it lead to. I'm probably just gonna skip to some of the results and give you pointers if you want to have fun and do it yourself, because otherwise I'm never gonna be able to cover some of what I want to cover. But so let's do a break now.